First things first, I'm sharing my screen. It's not what I was going to say, but quiz number 4 on Tuesday. Feels, pardon? Yeah, still out of the textbook. I will say, in terms of the textbook questions that I'm grabbing from, we're going to use the mathematical models, which are the ones on your formula sheets. Okay, and so those don't start until kind of the later half of the questions, right? And so those randomization ones and the bootstrap ones, you can kind of skip. Okay, you can do them if you want, but I'm not going to pull from those. Okay. So I'll only pull from the ones that talk about the mathematical model. Okay. And so kind of later textbook questions. There you go. Nice. Right. Later in the textbook, in each chapter. In each chapter. Okay. So mathematical models. Is what you're looking for. Okay. And Joya is going to be here for the quiz, not me. Fun, right? So I won't be here, but she will be able to contact me if you have a question. Okay. And so don't worry, I'll give her solutions, but it's not, you know, math is her jam, not stats. So can't expect her to know it on the fly, but she'll be here and you'll have the whole time to do the quiz, of course. And then when you're done, you're free. Okay. And so just take your time. You'll have a fresh copy of the formula sheet, but I figured I should bring some so that when you're studying, you'll know what you have and what you won't have, right? And so first, there's a note at the top. Everyone loves asking, what's Q? Any Q is 1 minus P. It's just shorthand, right? Q star, 1 minus P star. We don't have Q star, I guess. Q hat, 1 minus P hat, etc. Okay. And so I've outlined the things you need for a hypothesis test, right? They're the null hypothesis, what the test statistic is, right? How do you build a confidence interval? And then 2 sample proportions, right? We did a hypothesis test comparing these two, right? Proportions P1 to P2. If they're the same, which is what we start out assuming, right? Then P1 minus P2 must be 0. Right? And then our test statistic is a little bit bigger and it involves this P hat, but then notice I say where P hat is the pooled proportion estimate, and I give you all the different ways that you could find it, depending on, you know, what's easiest given your information. And then we can build a confidence interval for the difference in the proportions. And today, we see a brand new test statistic. Pretty fun. It's called the chi-squared. Chi is it's the Greek letter chi, and it's a chi-squared. Look at how itty bitty that is compared to the rest. So it's new, but it's kind of, I think, a little bit tighter. Also notice that we don't make confidence intervals, right? We only do hypothesis testing for chi-squared tests, okay? And we'll talk about why that is, but it stems from the shape of the distribution. So, can I close this now? We'll see. A two-way table. Let's start there. Inference still means hypothesis testing and confidence intervals, but for two-way tables, we're only going to do hypothesis testing. Okay? Now, a two-way table looks like this. It looks like two categorical variables. Right? Anything that kind of looks like variable 1 and variable 2. Just in general, maybe I have A, B, C, and maybe I have 1, 2, 3, 4 as generic categories. And so here we see that variable 1 has 3 levels, right? We've been calling them levels, okay, or categories. And variable 2 has 4 levels or categories. We've made tables like this, right? And so you can make a pivot table. Oh. Have a formula sheet. I can't remember if I said it, but you'll have a fresh copy of the formula sheet in the quiz and on the final exam, but it'll be bigger for the final exam. And so bigger, not bigger font though, turned out quite large, but that's nice. It's nice and readable, I guess. Okay. So, what was I saying? We want to compare variable 1 and variable 2. Oh, right. And you've made these tables already. You've made pivot tables, and we've looked at, okay, then I'm going to have some count in each combination of the variables, right? Variable A or category A with level 1, right? There's going to be some count here, some count, right? We have many counts in each of those cross sections. Okay. Now, what we want to know if we have this type of situation is we want to know if variable 1 is independent of variable 2 and vice versa, right? It goes both ways. Okay. And so here, our null hypothesis is that they are independent, right? Variable 1 and variable 2 are independent of each other. Or just generically, because it can go in either direction, the variables are independent of each other. We're used to seeing hypotheses with the proportions, right? The population proportion, how does it compare to some number? Or how does it compare to another population proportion, right? So this is a little bit different. Okay? And so what we want to know is, okay, are these variables independent of each other? What would that look like? If these variables are independent of each other, then we would expect, and pay attention to that word, right? We would expect the distribution of the counts for level 1, let's say, across all 3 levels of variable 1 to be roughly the same, right? And same thing for level 2 and level 3 and level 4, right? We could flip it for A as well, right? We would expect it to be kind of the same for A, B, and C. Right? And so, so that's what we're going to hinge it on. It's too early. So we're going to have observed counts, but we're also going to have expected counts. And just like we did with our Z scores, right? We had our sample proportion and we wanted to compare it to our hypothesized proportion. We saw, okay, how far apart are these things, right? And so now what we're going to do is we're going to have our observed counts and we see how far they are from the expected counts. Right? If they're not that far, then sure, these two things are independent of each other, right? And then the alternative is that they are not independent of each other, which is kind of boring, but easy. So the alternative here, I know I'm cheating. The variables are not independent of each other. If we take a peek at your formula sheet, right? That's what I gave you on your formula sheet, right? The variables are independent, right, of each other is kind of implied, okay? But because I give you this generic blurb, what I want to see on the quiz and on the final exam is something question specific, right? What variables are independent of each other? And so we've got an example. I'm going to use the example in the textbook just because it's all laid out and typed out and everything. And then I have a ChatGPT generated one, but it's pretty boring and missing a part, which I didn't catch until this morning because I didn't look at it. I trusted ChatGPT. Big mistake, huge mistake. I thought, oh, well, basic enough. Well, not quite. On the quiz / final exam, just coming down the pipeline here, you must word your hypotheses with question-specific variables or variable names, right? You must use question-specific wording. So for our first example, it's from an experiment that they did, and it was about iPods. I don't think they make, do they make iPods still? Probably not. We'll have phones now that do more. So anyways, iPods. Someone's selling used iPods. And so what they did was they had, I think, 219 participants who agreed, yeah, I'm gonna sell this used iPod, okay? But so they had, I guess, 219, or I guess they only need one iPod because it's just a prop, but they were asked to sell this iPod, right, to some stranger, okay? And so they were told that this iPod has frozen twice in the past, right, which is bad. And so the participants were incentivized to get as much money as they could for the iPod, since they would receive a 5% cut of the sale on top of $10 for participating. Okay. And so the researchers wanted to understand what types of questions would elicit the seller to disclose the freezing issue, right? And so kind of a level of trust. Unbeknownst to the participants who were the sellers in the study, the buyers were collaborating with the researchers to evaluate the influence of different questions on the likelihood of getting the sellers to disclose the past issues with the iPod. Kind of a gotcha moment, I guess. And so the buyers started with, okay, I guess I'm supposed to go first. So you've had this iPod for 2 years, and then ended with, one of these three, so randomly assigned to each buyer, right, was a general statement. What can you tell me about it, right? So no presumptions about kind of the state of the iPod. So that's kind of the neutral one. A positive assumption. It doesn't have any problems, does it? Right? Oh no, it's fine. Right? Makes it easier to say no. Negative assumption. What problems does it have? Right? And so depending on what question they asked, right, how likely was the seller to disclose the problem? Right? So now we have the question that the buyer asked, right? The general question, what can you tell me about it? Right? Then 2 out of 73 disclose the problem. It froze 2 times in the past. Only 2 people caved, right? Everyone else, oh no, it's fine, it's fine, it's fine. Whereas if the buyer said, it doesn't have any problems, does it? Then what's kind of interesting to me is that 23 out of the 73 who were asked that question said, oh, actually it froze 2 times in the past. Right? And so that's an interesting contrast to me. What's another thing? Already our guts are kind of saying, shouldn't these be more similar? And you're right, right? And so, and that's what our test statistic is going to leverage. Okay? Is that, okay, well, if the disclosure, right, is the same for all these questions, then I would expect these counts to be relatively similar, mostly because I see over here that there were 73 assigned to each question, right? And then the negative assumption, what problems does it have? Then everyone just spilled the beans, I guess. 36 out of 73, right? We can convert each of these, just like I've been saying, right? We can convert each of these to proportions if you want, right? 2 out of 73, right? 23 out of 73, right? Or as a proportion of who disclosed the problem, 2 out of 61, right? Lots of different proportions we could find. Okay, let us bring this in. We'll talk about it. You can ignore the totals, but we do need the totals later, right? But if we generically call this variable 1 and this can be variable 2, variable 1 has how many levels? Has 3 levels. Right? And variable 2, they either disclose the problem or they didn't. Right? So we only have 2 levels. Huh? So, like I said, we've got our kind of our gut reaction saying, this doesn't look like the variable 1, right, or the question variable is independent of whether they disclose the problem or not, right? And so let's start with our null hypothesis here. I'm gonna leave a little bit of room. No, I'll just copy and paste that table back in. I need a lot more room. But our null hypothesis with question-specific variable names would be the question asked, right, is independent of whether the seller discloses the problem or not. Okay? Or you could phrase it, right, disclosing the problem is independent of what question was asked. Those two I would consider equivalent. Okay? because the independence goes both ways. So let's say whether the seller discloses the problem or not is independent of the question asked. And I get to cheat because I'm on an iPad. But the alternative hypothesis then is whether the seller discloses the problem or not is not independent of the question asked. So we just do the flip side. So you have to use question-specific variables. Right? But as long as you're talking about, okay, these two things are independent of each other, that's fine. Sometimes the wording gets a little bit weird, right? But you could say something as simple as the question asked is independent of disclosure, right? Just because it's our first kind of foray into this new question type. Okay. Like I said, I want to copy this because that's going to be step one, right? Step one in a hypothesis testing question. State the hypotheses. For step two, do the test or calculate the test statistic. I'll say calculate the test statistic. Boring. We're going to rely on, so we have our observed counts, right? But we want to compare them to the expected counts. I'll use green. We compare our observed counts to the expected counts. The expected counts if the null hypothesis was true, right? We do all our hypothesis testing assuming the null hypothesis is true, and so that stays the same. So we compare our observed counts to the expected counts. Bless you. Assuming H naught is true. Now I give you the formula on the formula sheet for each of the expected counts, but let's talk about kind of why that is. So for this 2, let's talk about our expected count, right? I have an observed count of 2. I suspect it's a little bit low because I expect a higher count. And so the expected count is going to be, what if I take the total, right? Overall, right? Disclose the problem. Who cares about what the level is, right? The probability of disclosure, right? 61 out of 219, right? And then I can multiply that by the sample size in each of the questions, right? And distribute that across each of the questions. And so we have the overall probability of disclosure, which is 61 out of 219, 219, right? Which is this guy over this guy. If we ignore the question type, then 61 out of 219 disclose the problem, right? Which is not the same as 158 out of 219, right? So I'm expecting a smaller proportion or percentage of people to disclose the problem, right? In fact, I'm expecting roughly what? 61 over 219. 61 over 219, roughly 0.2785 to 4 decimal places. So 27.85 is what I would expect in each of those question groups. Which I can then say, okay, then I expect, if it doesn't matter which question you were asked, I would expect 27.85% out of 73 to disclose the problem, right? It's nice because we have the same sample size in each group, okay? And so then I would expect the same count across the board, right? We don't have to have the same sample size in each question, okay, which we'll see. Okay. But what this means is, therefore, for each question, I expect 27.85% of sellers to disclose the problem. Oops. Which also means the opposite of that, 1 minus 0.2785, is how many I would expect not to disclose the problem. Right? It doesn't have to be even that way. But it would have to be even across the disclosure here. Okay. And so what can I do? Okay, if I have 73 sellers that were asked that general question, then I can multiply that by 0.2785. Okay. And so we can say 73 sellers times 0.2785, 73 times 0.2785, I expect 20.3305 to disclose the problem. Expected to disclose. When asked the general question. Now this number would be the same across the board because I had 73 sellers in each question type, right? And so I had 73, 73, 73. And so then I would expect 20.3305. Now, there's a desire probably to round that, right? Say, well, I can't expect a not whole number to disclose the problem. But the expectation, as we've seen, can be a fraction, okay? And so it's because, okay, this is what I would expect to see if I had 73 sellers sampled an infinite number of times, right? And so this is my expectation overall, right, over time, but it's also our expectation to compare to 2. Yeah? And so here, I'll make a note. We do not round expected values. Huh? Oh, yeah, so here I use this rounded value, but if you use the proper value, it'll be slightly different. Yeah. So what did we do? All right, let's build on that. This we can rewrite as 73 times technically 61 over 219. Right. Now, if I'm multiplying and dividing, that's going to be the same as everything over 219. And so how we usually summarize this is that this is the, what was that, 73? That's your row total. Right? Your row total times your column total divided by your grand total. Right? And so here, this is your row total divided by, or times your column total divided by your grand total. And that's how we find your expected count. Oops. Each cell, right, is going to have a different combination of row totals and column totals, unless some of them are the same, but they're not necessarily the same. In our case, they are the same, but they're not necessarily the same. Yeah. And so, all right, on our formula sheet, I give you E, which is the expected count of each cell. Expected count of each cell. So you're going to be able to calculate the expected counts, and definitely a task for Excel, right? We can do it by hand, but I'll show you some Excel options. Because now what would you have? Well, pointer. Each one of these cells has an expected count, right? You ignore the totals, but we need the totals because I need them to find those expected counts, right? But when I think about how 2 compares to 20.33, right? That's quite a ways off, okay? And so then I say, that seems strange, right? 23, right? This 23 would have the same expected count just because it has the same row total and the same column total. So 23 compared to 20.33 is not that far in my kind of gut reaction opinion, right? And so we need some measure of spread to determine, okay, well, is it far or is it not far? Okay. And so what we use as our spread, kind of confusingly, is the expected value. So just take that as fact. Okay. So, and then 36 compared to 20.33 is a little bit on the higher end, maybe. We'll see. Okay. And so what we're going to be able to do is we're going to calculate how far are each of these observed counts from the expected counts, right? But some of them are going to be below and some of them are going to be above. And spoiler alert, we're going to start adding those deviances up. Now, if we have negative deviations and positive deviations, we've seen that before with the standard deviation, right? We need to figure out a way where they don't cancel each other out, right? And kind of the most common way of dealing with that is to square those deviations, right? Squaring things makes them positive, right? But it also amplifies large deviations, right? You're kind of penalized for those large deviations, okay? And so that's what we're going to do. Okay? So our test statistic, our brand new test statistic, I should say new test statistic, fun, is called the chi-squared. So this is spelled chi, but don't say that. You're going to read it as chi. So it's a Greek letter chi, chi-squared. Now, chi-squared is a slippery little bugger. And I say that because the shape of the chi-squared depends on what we call the degrees of freedom. Okay? And so the shape of chi-squared depends on the degrees of freedom. Luckily for each problem, the degrees of freedom is fixed. So the shape will be fixed for each problem, but it'll shape shift depending on your degrees of freedom. So what does it look like? I know you're dying to know. What could it possibly look like? Here. Oops, I should have the figure text as well. Otherwise, it's just a little image. So without knowing what the degrees of freedom are, although if you do some sleuthing on your formula sheet, right, it's on there. But if you have 2 degrees of freedom, then the shape looks like this, right? Nice and compact here, and then it slopes down almost immediately. And what's interesting about the chi-squared is it starts at 0, right? And that's because our chi-squared, right, we said we're going to square our deviations, and so they're not going to be able to be negative. Okay? And so it starts off kind of smushed at 0, and then as you increase your degrees of freedom, right, it starts to tone down, right, and just kind of level out, and the center shifts to the right more and more as you increase your degrees of freedom. Okay, and then eventually, if you have a really large degrees of freedom, right, it tends towards a normal distribution. You need a really large degrees of freedom though, and it won't be quite there. Okay. But in general, right, the chi-squared, when I draw a chi-squared, I draw it kind of like 4 degrees of freedom, right? Because we just need it to visualize what we want. Okay. So some chi-squared facts, let's jot those down. Chi-squared facts. 1, it starts at 0. 2, as the degrees of freedom increase, right, it approaches a normal distribution. It approaches the normal distribution. which means the center gets kind of pulled out towards the right as we increase our degrees of freedom. Now, the chi-squared, right? We're used to having to pay attention to, do I want the upper tail or the lower tail? Or if I have a two-sided test, I want both tails, right? For our p-value. Yeah. But for a chi-squared, the p-value is always going to be the area in the upper tail. Yeah. And so, because here at 0, there is no lower tail, right? And so our p-value just is going to be the upper tail. So let's say maybe here, right? This is going to be my p-value. The p-value is always the area in the upper tail. Notice that the scale of chi-squared is different than what we're used to seeing, right? A z of 10 would be considered very, very, very large, right? And here, depending on your degrees of freedom, right? A chi-squared of 10 at 2 degrees of freedom would be very rare. At 4 degrees of freedom would be kind of relatively rare, but at 9 degrees of freedom, not very rare at all, right? And so our chi-squareds, right, depend on the degrees of freedom. Let's talk about this. Since I've said degrees of freedom so many times already, how do we find the degrees of freedom? So for us, the degrees of freedom which we abbreviate DF, is going to be, for a two-way table, the number of rows minus 1 times the number of columns minus 1. Number of rows minus 1 times the number of columns minus 1. So if we go back to our question that we're working on, how many degrees of freedom do we have? If it's the number of rows, now we don't count the total rows because usually we have generated those, right? But we have 3 rows and we have 2 columns. So in this case, for our example, the degrees of freedom is 3 rows minus 1 times 2 columns minus 1. 2 times 1, I have 2 degrees of freedom. Right. So the shape of our distribution looks like this. Right. 2 degrees of freedom. Now imagine, what would your table have to look like? There's a couple of different options to get 9 degrees of freedom. It's actually kind of difficult, right? You'd have to have a very large table. At smallest, a 4 by 4, right? Or some, combination of that. And so, right, 4 minus 1 times 4 minus 1 makes 9, right? That's really large. That's a large table. So now we've got our degrees of freedom. And of course, it's on your formula sheet at the bottom. What am I skirting around here? I'm skirting around the actual chi-squared. We'll get there soon enough. Right, on your formula sheet. I almost changed it to R minus 1 times C minus 1, but then I thought, I'll keep it. Number of rows minus 1 times the number of columns minus 1. but usually I use this shorthand, r minus 1 times c minus 1. Okay, good. I think we're ready. So for our test statistic, I know we're only in step 2, test statistics still, but we're establishing the rules of the game. Now, the chi-squared test statistic computes the deviations, right? Computes how far the observed value is from the expected value. Or I'll say compares. I think I've already written it, but I think it's worth writing again. Compares how far the observed count is from the expected count. On your formula sheet, I opted to ditch all subscripts, even though there's a lot. I just said add these all up. So the chi-squared is what you're going to calculate. You take your observed minus your expected, then you square it, and then you divide by the expected value. You do this for each cell, and then add those all up. So here, calculate this for each cell. I'll say step number 1, and then step number 2, add them all up. Which requires, okay, so to calculate the observed minus the expected squared divided by the expected, you need the observed count, which you'll have, but you also need those expected counts, right? And then you're off to the races, right? You need your observed count, your expected count, and then you can make a new column where you square it, and then a new column where you divide by E if you want to break it down nice and slow, or I would probably recommend using Excel. I'm going to make you show me that you know how to find the expected values, okay? But then I'll give you the chi-squared. Okay? And so, so you won't have to do it, because what would it look like for our table that we're working on, right? The dishonest sellers, let's call them. You would have, where is it? So here, we could calculate the observed count, and then we have our expected counts. The observed count and then our expected counts are in the brackets, right? And we want to see how far are each of these from the expected counts, right? And because we have the same count total here, the same row totals, we expect the same distribution across each of the questions, which is not necessarily the case always, but in this case it is. So what would we need to do? Our chi-squared would be 2 minus 20.33 squared divided by 20.33 plus, and I'll work across the rows down. It doesn't matter since you're adding them up anyways. Plus 71 minus 52.67 squared divided by 52.67 plus 23 minus 20.33 squared divided by 20.33, blah, 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 blah. That's just math. We can do that, right? Boring. I'm going to steal it. So for each, the observed count minus the expected count, maybe I'll snag all of this. More room. Even she quit. But we get a chi-squared of 40.13. Yeah? And so right here, this is what we did. 2 minus 20.33 squared divided by 20.33. That becomes a number. Each one of those cells is going to generate this squared deviation. It's called the Pearson residual, but that's okay. You don't need to know that. And then we add those all up. And that makes our chi-squared. Just like a z, a large chi-squared is kind of evidence against the null hypothesis, but we don't know if this is big or not because we need our degrees of freedom to determine the shape. Now from this image, right, if we have 2 degrees of freedom, we're on this sharp, sharp curve. And it looks to me like 40.13 is pretty rare, right? I'm even off the chart here, right? And so looking at this scale, right, I expect my p-value to be very, very, very small. But let's find it. This is step 2 done. But like I said, I will make you show me how to find some expected counts. Okay? But I will then say, now assume your chi-squared is this. Okay? And so then I give you the chi-squared just like we did here. Because this is just kind of like plug and chug and math. Okay. Let's see here. Step 3, find the p-value. Right. If our chi-squared, we said we have, recall, the degrees of freedom is 3 minus 1 times 2 minus 1 in this case. So we have 2 degrees of freedom. So our shape looks something like this. Okay. Here's 0. Here's all my chi-squareds. And at some point here, chi-squared is going to be 40.13, right? The value we calculated. So this tail area is the p-value. Right? I find it gets a little bit messy because if we think back to our alternative hypothesis, right, it was that these two things are not independent of each other, which would typically be reflected by a two-sided p-value, right? But now my p-value is just the area in the tail, right? And so we don't make that connection anymore, right? Because I don't have the symmetry, right? And also looking at this shape, this is the reason we can't build a confidence interval anymore, right? Or reasonably. And so because we need symmetry to build an interval, right? And so where's the symmetry here? Not here. No. So in Excel, you're going to use the, I think it's called chi-squared dot dist. And then I encourage you to just use the right tail. It does have a chi-squared dot dist, but chi-squared dot dist, just like all the other chi-squareds, right? You feed it a chi-squared and it gives you the area to the left, but that's not what you want, right? And so they've generated this special right tail, which is the p-value that you want. Instead of having to do the 1 minus chi-squared dot dist, it just saves you one step. And so here, it's going to take your chi-squared, and then it's going to take your degrees of freedom. It needs to know, hey, what shape am I working with? Right? What's cool about the chi-squared is, unlike the normal distribution needs to know the center and the spread, right? Those two parameters, whereas the chi-squared only needs to know the degrees of freedom, and then it knows what shape to take on, right? And so that's kind of cool. And so if we do chi-squared dot dist dot right tail, and maybe I'll clarify this of chi-squared and the degrees of freedom is the same as 1 minus chi-squared dot dist of the chi-squared at that degrees of freedom. Right? So the right tail just does that 1 minus for you. Use whichever one. But for the output on the test, or sorry, quiz, you didn't hear me say test. No. Sometimes I have students freak out. Is it a test or a quiz? You need to tell me. Yeah, it's worth 10%. I don't know what to tell you. You decide. Chi-squared dot dist dot right tail. Right, this is the one that I'll use because it's a little bit cleaner. Okay. But in life, if you want to use the 1 minus just for kind of continuity from the normal, that's cool. So where's my Excel here? Conveniently, I was doing chi-squared's tests of independence in a different class yesterday. So let's see here. Equals chi-squared dot dist dot right tail. Chi-squared, we had 40.1 Q3.1, hey, 1.3, and it needs our degrees of freedom. Whoops, 2 degrees of freedom. Itty bitty. Can I make it show? No. I have to deal with that scientific notation. That's okay. I'll screenshot this. Bring it in. Oops, that's not how we do it anymore. This tells me that the p-value is 0.000 blah, 8 zeros, 193144. Very, very small. So this tells me that the p-value is 0.1234567 uh-oh. Not gonna have room for my 193144. Very, very small. You can think of this as the probability that the null hypothesis is true. right? We did everything assuming the null hypothesis was true. And so if it helps you to think about the p-value as the probability that the null hypothesis is true, right? That helps us kind of remember, okay, if the probability that those two things are independent of each other is that, I would say probably not independent, right? And so that's why we reject H naught. In fact, as a threshold, right, we use 0.05 or 5% as our threshold, where we say, kind of unlikely, I'm going to reject H naught in favor of H. So very, very, very small, which was confirmed by what we saw on that graph, right? When we tried to put 40 on our chi-squared with 2 degrees of freedom, right? We were way off the page, right? And so, and that's what this is saying. The area in the tail above 40.13 is this small, right? Chi-squared still keeps going to infinity, just like Z's do, okay? But the area in the tail is very, very, very small. Okay? So now we have a p-value. That's great. This tells us, right, if our chi-squared starts at 0, and I have a chi-squared of 40.13, then this area in the tail is 0.000. Uh-oh, I should just copy it. That's that area in the tail. Whereas we said, okay, usually at an alpha level of 0.05, right? Once I cross this threshold, right, 0.05, then I'm going to reject H naught. So after this point, I'll say alpha is 0.05, we reject H naught. Anything before then, we fail to reject H naught, or we don't have enough evidence to reject H naught. We can use the inverse of the chi-squared to find what chi-squared we would start to reject H naught at, right? Let's see. Let's do equals chi-squared dot inverse. Oh, there's even an inverse dot right tail. Any guesses? Pretty sure I give it the area in the right tail and it returns the chi-squared that makes that happen. So let's do that. The probability is going to be 0.05, and I still need 2 degrees of freedom. This tells me that a chi-squared past 5.99, then I would start rejecting H naught. So you can use either method, right? We tend to use the p-value approach because it's considered more formal. And especially if you're publishing and things like that, you should probably use the p-value approach. But this is called the critical value approach, right? Where you say, hey, any chi-squared past this point, I reject H naught. And they do the same thing, right? I'm forcing the area in the tail to be 0.05, or I'm finding the area in the tail and then comparing it to 0.05. They do the same thing. I'll screenshot this. At the end of every term, I think, wow, I should really delete all those photos because it's just a bunch of screenshots. And then I never do. So there's so many boring screenshots. No one disagrees. They're not boring, Emily. right? This tells me that this chi squared, right, would be roughly at 5.99, right? Any chi squared larger than 5.99, we would reject H naught. Kind of two ways of doing it, doing the same thing. I'm going to stick to the p-value approach, right, from here on out, but it's nice to see, and I think it makes a nice connection, and we can do the same thing for z's, right? We could say, okay, I could force the area in the tails or tail to be 0.05, then what z makes that happen, and then if my z is bigger than that, then I reject H naught. And so we can do that for z's as well. Okay, we're ready for our conclusion. Because now I have my p-value. Step 4 is my conclusion. This is your time to shine and show off all the things that you worked so hard for, right? Tell me what your p-value is. Tell me what you're comparing it to, right? Tell me, okay, then I have enough evidence to reject H naught, or you don't have enough evidence to reject H naught, but your conclusion has to be in terms of the null hypothesis. Why? Because we did all our testing assuming the null hypothesis was true until we found so much evidence against that, then we reject it, right? And so we had to assume that these two things were independent of each other until we said, okay, well, that's unlikely, right, given our p-value, right? And so let's see here, your conclusion. Since our p-value of, I wonder if it's still in there, paste, haha, make it blue. There, like nothing ever happened. All right, tell me what it is. You worked hard to get that number. I'll give you the output, the Excel output on the front page again, but you still have to know which one to grab. So since our p-value of basically 0, not 0, because you'd have to go to infinity to be 0, right? You're allowed to say approximately 0, right? But not 0. So since our p-value of very small is less than our alpha level of 0.05, right? We weren't told to use anything but the default, which is 0.05. We have enough evidence to reject H naught. If I'm rejecting it, I can offer up the alternative, right, in favor of the alternative hypothesis. But you don't have to, right, because I don't want to see, you know, I don't have enough evidence to reject HA or anything like that. Your conclusion is in terms of the null hypothesis. Okay? And so if it simplifies things, you could just put a period here, right? You either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. And those are your only two options. Okay? But I'll say in favor of HA. If I'm opting for the alternative hypothesis, then I can just state that as my conclusion. Right? Therefore, been a while. Let's see here. Where is it? I'll put it here. Therefore, whether the seller discloses the problem or not is not independent of the question asked. Doesn't have to be fancy. You can just state your alternative hypothesis, right? How you wrote it, or you can reword the question as an answer. They'll usually be quite similar. Right? But for simplicity, right, I'll just take the alternative hypothesis. I want to highlight probably again, there are 3 parts to your conclusion, which means I make it 3 marks, right? Usually 3 marks out of 7. 2 for your null and alternative hypotheses, because that's where you establish, hey, this is what I'm about to do. Okay. 1 for your test statistic. It's a lot of work, but it's not hard, right? And 1 for your p-value, and then 3 for your conclusion. Okay. And that's because it has these 3 parts. Part 1, compare your p-value to the alpha level, right? Is it less than the alpha level or is it not less than the alpha level? The second part is, what's your conclusion in terms of the null hypothesis? Do you have enough evidence to reject H0, or you don't have enough evidence to reject H0? So here, your conclusion in terms of H0. Right? And that's because we did all our testing assuming the null hypothesis was true. And then finally, the one, because you've done a lot of work at this point that people love to forget, the conclusion in terms of the question, right? You have to answer the question. Conclusion in terms of the question. Three parts, 3 marks. So this is 3 marks, usually out of 7. Two marks for your null and alternative hypotheses, right? Often because if you kind of set out on the wrong null and alternative hypotheses, if you're able to stick with it, which is difficult if you pick the wrong null and alternative hypotheses, but if you're able to stick with it and kind of plow through, then that's worth more than just kind of jumping around, right? So once you've decided what type of question it is, right? On quiz 4, there's only 3 types, right? So once you've read through the question and you figure out, okay, what type of question do I have? Then you stay in that region of your formula sheet for that entire question, right? And so, but there's a lot of places where the null and alternative hypotheses can go wrong. And so I make it 2 marks because it's very important. And then I make 1 mark for your test statistic. And that's because there's a lot of calculations often, right? And little typos shouldn't really bog you down. As long as you follow through with whatever test statistic you found, then I'm happy. Okay? In fact, if you're completely running out of time, this is a good place to say, I don't have time to calculate my test statistic. I'm going to let my Z be this, right? Let it be 2.5 or something reasonable. Right? I'm going to let my chi-squared be 10, right? Just pretend. And then you don't get that 1 mark, but that's only 1 mark, right? And then you can keep going and you can find your p-value and you can find your conclusion, right? Which are your money makers. So for another 1 mark is the p-value. Again, if you're able to find your test statistic, but you can't find your p-value, just tell me, I'm going to use a p-value of this, right? And then use that for your conclusion. You can't get the mark for the p-value, obviously, but you can get full marks if you follow through properly with your conclusion, okay? And so you're allowed to do that, right? Just kind of say, oh, okay, I won't have time to find that value. I'm going to assume it's this. Now, one of the things is it has to be kind of a reasonable value, right? P-values have to be between 0 and 1, right? And I don't know, practice with a p-value and have a default p-value in mind, right? And so, right, could do that. 3 marks for your conclusion. Right, and you have to touch on all 3 of those things. Okay. Wow, time flies. Okay. But it's our new test statistic, and so that's pretty exciting. Okay, so on the quiz, on quiz 4, I will also ask you what type of question it is for 1 mark. So that's in addition to those parts, okay? And that's really just to kind of highlight to yourself that that's the region of your formula sheet that you're going to be working in for that question, right? So it should be a freebie 1 mark, right? But I do it nonetheless. I think that's nice. So on quiz number 4, you will need to tell me what type of question each question is. Hey.
I grab the chairs.
Go for it. Do you need a hand?
Okay.
The busted ones?
Yeah,
Yeah. Nice.
Seems like it's room for you. So.
Well, maybe good for crafting or something.
Yeah. That's not sure. If, somebody failed the test.
Oh, yeah. All fixed up.
Awesome.
Thank you. Nice. Well, spring cleanup. So you'll need to tell me what type of question each question is for 1 mark. And your options for this quiz are a 1 sample proportion, two sample proportions that you want to compare, how can I keep this on? You know what? Let's try to bump this up because I want to have it on the same page here. Or I called it the chi-squared test for independence on your formula sheet, so you can call it that type. The chi-squared test for independence, which is what we're doing. Now this was chapter 16, chapter 17, or chapter 18 today? In case that helps, right? Just in case. So really what you're doing is you're telling me, for this question, I'm going to be working here on my formula sheet, right? And I'm just trying to help you focus for that question, right? Which area to be on. So it should be a freebie 1 mark. Okay. I'm not going to make you check the conditions, right? On the quiz and on the final exam, right? I'll say you may assume the conditions for inference are satisfied, but we should probably know what the conditions are in case we're out in the real world and we have to check these things. Now the conditions for a chi-squared test, and this is for any chi-squared. There are other chi-squared tests. There's a chi-squared goodness of fit test. Yeah. There's a chi-squared test of homogeneity, right? And so, but this is kind of the biggest one. And so that's the one that we learn about. And then you compare it down, right? To compare the goodness of fit, which would be, okay, if I expect an even distribution in the proportions or the counts that disclose the problem, right? Which is what we started with, right? Then you can ignore that second column. Okay? But we just went for it with a test of independence. But there are other chi-squared tests. Okay? So the conditions. All the counts have to be independent of each other, right? That's that independence condition that we've been seeing. So independence. Now, in our case, we're doing a chi-squared test of independence to see if those variables are independent of each other. And so that's not what we mean, right? But we do mean that each of the counts that we've recorded, right, they have to be independent of each other, right? So each observation is independent of the rest. Again, just like any independence, this is accomplished by randomly sampling or randomly assigning treatments. And so here, random sampling or randomly assigning treatments. Assigning treatments. In our case, right, I think it maybe even said, right, what follow-up question, the general question or the positive or the negative kind of follow-up question was randomly assigned, right, to each seller. And so, okay, you're going to get this one, you're going to get this one. And so then we can assume that they're all independent of each other. And we're used to big mumbo jumbo conditions, right? Our sample size conditions. So yeah, we have to have at least 10 expected successes, 10 expected failures, or observed successes, observed failures for each group if we have 2 groups, right? We're used to these kind of big conditions. But the next condition is our sample size condition. And all it is we need at least 5 expected counts in each cell. And so at least 5 expected counts in each cell. which means that before you can check the conditions, you would need to calculate those expected counts. So let's go back to our expected counts. And I really hope that they're all big enough. Phew. 20, 20, 20, 52, 52, 52, all greater than 5. And so we're allowed to use that chi-squared distribution. Right. How would you get something less than 5? It would be if one of these groups was very, very small compared to the other two or other groups, I should say, right? Then you would expect a small count. So you need kind of, that's why we call it the sample size condition, right? I need a big enough sample in each of these groups or categories to be able to detect the observed minus the expected difference. Okay. Nice. Anything else I wanted to say before we got this failed ChatGPT example? Any questions before I bring that one in? Okay. Let's see here. Copy, because it turned out all weird. Paste. Here's another example. Now I want you to think about why this is a bad example, right? And what do I need to change? In fact, maybe let me show you the rest of it. And I kind of quit fixing this, but maybe I shouldn't have. Hey, where's this? How about this instead? We make our own. So the table that we were given looks like this. Plant A, plant B. Meets safety standards or fails safety standards. Oops, fails. $290, $30, $255, and $45. Why is this a bad example for a chi-squared test of independence? I could just compare the sample proportion of plant A that fails maybe or meets the standards, it doesn't matter, right? To the proportion of plant B that fails the safety standards, right? This would be a pretty good two-sample proportion question, right? To make it worthy of a chi-squared test of independence. Now you can do a chi-squared for this, but I would say just stick to the simpler normal distribution and use a two-sample proportion question instead. Okay. So now I'm going to tack on a plant C from 3 water treatment plants, plants A, plant B, and plant C. And records whether each sample meets safety standards. Well, that C looks weird. And then I'll make up some numbers. Let's do 215 and 25. And I'll delete this. And then the question is this. At a 5% significance level, which we've seen is the alpha level, right? And so this means that alpha is 0.05. is there evidence of an association between the treatment plant and whether a sample meets safety standards, right? Or is the distribution of whether they meet safety standards or not, is it kind of even across the board, which I would hope, right? If you have a plant that's kind of famous for not meeting safety standards, that's bad, right? Then it's not independent anymore. Yeah. And so what we need is we need the totals. Okay. Some proportion of the grand total meets the safety standards, which is going to be 290 plus 255 plus 215. Oh, a nice, beautiful 760. 30 plus 45 plus 25. Wow, almost like I planned it. I did not. 860. Huh? 290 plus 30. 320. Here's the total. 255. Oops, not times, but plus 45. 300 and 215 plus 25 is 240. I sampled a lot fewer from plant C. That's okay, right? Before we had an even distribution from each of those question types. And that's because that's how we usually set up experiments. There's no reason to give ourselves an uneven distribution, but maybe it's harder to get to plant C and take a proper sample from plant C or something like that. And so then we can handle having different sample sizes in each group, right? Or from each plant, right? And now, okay, we want to know if there is evidence of an association. Now, an association would mean that they are not independent, right? However you want to word this is fine by me, right? As long as you're talking about, okay, the plant and whether it meets safety standards or not, they either are independent or are not independent of each other. Okay. And so is there evidence? Whenever you see that, you're going to have to do a hypothesis test. And a dead giveaway of the type of question that you have, oops, is if I give you a two-way table, which I will, right, and right, ask you to do a hypothesis test for this quiz, it can only be a chi-square test of independence. Right? So let's do the type of question is a chi-squared test of independence. And that's because we were given a two-way table. Not because of that, but on this quiz, it'll be the dead giveaway. You could, I'm not going to do it because it's really mean and she doesn't do it in the textbook, so I'm kind of limited, but you could ask a one sample proportion question, right? Is the proportion of safety checks or whether they meet the safety standards or fails the safety standards significantly more than what's 100? 100 divided by 860 is roughly 11.6%. Is it significantly more than 10%? Right, that would be bad. That's a one sample proportion question. Right? If you want to compare the proportion from plant A that fails the safety standards to the proportion from plant B that fails the safety standards, right? 30 over 320 versus 45 over 300, that makes it a two sample proportion question. And now here we are looking at considering kind of the two variables against each other. So you could, but I'm not that mean. But it's nice practice. Okay. To check our conditions, which I will do if there's time, because they're so brief, but we need the expected counts, and I need the expected counts for the test statistics. So I'm going to hold off on checking the conditions until I have those. Or the alternative would be to calculate them right away and check the conditions, but state the hypotheses. Your null hypothesis. From your formula sheet, it just says variables are independent. You need to elaborate a little bit more on that, but you can take, there's no association between the treatment plant and whether a sample meets safety standards, right? Just kind of take the neutral statement of the question. That's one way to do it. Or if you want to say the plant and whether it meets or fails the safety standards are independent. Right? Two ways that you could phrase it. But let's do it by rephrasing the question. There is no association. No association, which means that they are independent, right? Between the treatment plant and whether a sample meets safety standards. And then the alternative is going to be there is an association between these two things, right? Which is kind of how the question was worded. Most often, what we want to know is about the alternative hypothesis, but we have to assume that the null hypothesis is true. We have to start somewhere, and then we can talk about the alternative. Because I'm running out of time here. Paste. The alternative. There is an association between the treatment plant and whether a sample meets safety standards. Let me delete this. Can I? Nope. I want to delete all this. Come on. Okay. I'll delete the whole page. Watch me. Ta-da. There. A little bit wordier than we're used to for our hypotheses, so it takes some getting used to, but step 2, we have to calculate the test statistic. Which requires our expected counts. Requires the expected counts. This one is a little bit big, and I'm wishing that I had prepped it ahead of time. Oh well. because then I would just have it done in Excel already. Not too bad. It's only 6 calculations. How do you find the expected count for this first cell? You have to have the row total times the column total divided by the grand total. Right. And so let's see here. 320 times 760 divided by 860. I would expect 282.79. Let's keep 2 decimal places. Now, each of these expected counts are all going to be different. So 320 times 100 divided by 860. Oops, not cosine. Math. I expect 37.21. Rounding to 2 decimal places. 300 times 760 divided by 860. 265.12. 300 times 100 divided by 860. 34.88. 240 times 760 divided by 860. 212.09. And finally, 240 times 100 divided by 860. 27.91. We did some rounding, but these expected counts should roughly add to the total. If you've done some rounding, you can be a little bit lenient, but right, don't round too much. Okay, so now we've got our observed and our expected counts, and our chi-squared would be the sum of the observed minus the expected for each cell squared divided by the expected. I don't feel like doing that with 1 minute to spare potentially. And so we can also use in Excel, there's a chi-squared dot test function. So the chi-squared dot test function takes the observed counts, the observed, which would be, so you would put them in a table like this because it needs to know the number of rows and the number of columns to internally calculate the degrees of freedom. And I think it's pretty weird, but we need to give it the expected counts, even though it should be able to take the observed one and just calculate them. But I guess it needs a separate table with the expected in the same layout, but then it'll return the p-value. So it's kind of like 2 steps in one, right? Bypass everything, but you do need to calculate those expected counts. I've got in the first sheet here, these are for a different example, but it would need the counts like this, the observed counts, and then the expected counts, and then the chi-squared dot test has, does it highlight them? It does, but it wants me to type stuff and I don't want to. So then you give it the the area with the observed counts, comma, the area with the expected counts, and it spits out, oops, oh no. The p-value. So a conclusion. How about I'll use Excel, I'll do the calculation for the chi-squared and the p-value, but let's say for practice, pretend the p-value is 0.0795. And just draft a conclusion based off of that. But then I'll find the actual p-value, but I'll post the conclusion for this assumed p-value, right? So you can check your conclusion, right? Practice your conclusion, and then, but I'll do the actual conclusion as well. And try checking the conditions. But we have those expected counts now. They're all greater than 5. And we assume that a measurement from plant A that meets the safety standards is independent of all the other observations, which is pretty reasonable, right? You don't have a measurement from plant A also popping up in plant B, right? Okay. With that, I release you. Enjoy your weekend and enjoy the quiz on Tuesday. All right. Stop this.